Welcome to day 9 of our statistics series, Skewness and Kurtosis. If you've ever asked, why does my data look lopsided? Why are there so many extreme values? Or why does my machine learning model perform poorly on this data? The answers often lie in two fundamental shape descriptors, skewness and kurtosis. In this video we will master both concepts from the ground up. Explore their formulas, build visual intuition, walk through real-world examples, and understand exactly why the shape of your data distribution can make or break a machine learning model. Here's a critical insight that trips up many analysts and data scientists. Two datasets can share identical mean, median, and standard deviation yet look completely different when visualized and behave very differently in models. If you only report the mean and standard deviation, you miss crucial shape information. This oversight leads to underestimating financial risk. Many 2008 financial crisis models assumed normal distributions and missed the fat tails. It causes machine learning models to fail on rare but real extreme events. It invalidates parametric statistical tests that assume normality. Skewness and kurtosis are the two measurements that capture what summary statistics hide: the asymmetry and the tail behavior of your distribution. Skewness is the statistical measure of asymmetry in a distribution. It tells us where the data is leaning to one side of the mean. The formula divides the third central moment, the average cubed deviation from the mean, by the standard deviation cubed. Cubing the deviations is the key. Positive deviations cubed remain positive. Negative ones remain negative. So the sign of the result tells us the direction of skew. The denominator normalizes the result, making it scale independent. You get the same skewness value where the data is in centimeters or kilometers. There are three possible skewness scenarios, and recognizing them visually is an essential skill. The middle curve, the symmetric normal distribution in teal, has skewness of 0. The mean, median, and mode all coincide at the center. The left skewed distribution in purple has negative skewness. Its tail stretches to the left. The bulk of data clusters on the right side. The mean is pulled left of the median, which is left of the mode. The right skewed distribution in orange has positive skewness. Its tail stretches to the right. The bulk of data clusters on the left side, with the mean pulled rightward by outliers. A simple memory trick: the tail points in the direction of the skew sign. A crucial relationship worth memorizing. In a right skewed distribution, the order is mode, then median, then mean. The mean is dragged farthest into the long right tail. In a left skewed distribution, the order reverses: mean, then median, then mode. This means that for positively skewed data like incomes, the median is always a more representative center than the mean. That is why economists report median household income rather than mean income. How do we interpret the skewness number? A value of exactly 0 means perfect symmetry. Values between -0.5 and +0.5 are considered approximately symmetric. Most parametric tests will still work fine. Values between 0.5 and 1.0 in absolute value signal moderate skew. You should consider a data transformation. Values above 1.0 in absolute value indicate severe skew. A transformation is very likely necessary before applying parametric models. These thresholds come from Bulmer's 1979 guidelines and are widely adopted in applied statistics and data science. In Python, you can compute skewness with just one line. CP, stats, skew of your array. Or data frame, skew. In pandas. Let's go deep on positive skewness. The right skewed distribution. You can see the long tail extending to the right. Notice the three vertical lines. Mode in green is the peak. The most common value. Median in yellow sits further right. Mean in red is dragged furthest right by those high extreme values in the tail. This ordering, mode, median, mean from left to right, is the signature of positive skew. In real life, income distribution is the perfect example. Most people earn moderate incomes. But billionaires create a long right tail that pulls the mean salary far above what a typical worker actually earns. House prices, insurance claims, social media followers, earthquake magnitudes, all exhibit this same pattern of many small values and a few extreme large ones. Negative skewness. Left skewed data is the mirror image. The long tail extends to the left, and the bulk of data piles up on the right side. Here the order reverses. Mean is dragged furthest left by extreme low values. Median sits in the middle. And mode is the rightmost peak. Real examples include retirement age. Most people retire around 65. But a few retire very early at 30 or 40, creating that left tail. Easy exam scores cluster near 100, but some students score near 0. Bear market returns are left skewed. Small daily gains are common, but catastrophic losses can be extreme, creating dangerous left tails that financial models must account for. Let's compute skewness step by step for a familiar dataset. Our data is 2, 3, 4, 4, 5, 5, 5, 6, 7, 8, 12. Step 1. Calculate the mean. Sum is 61. Divided by 11, giving 5.55. Step 2. The standard deviation is 2.6064. Step 3. For each value, compute the cubed deviation from the mean. Notice how the outlier value of 12 produces a very large positive cubed deviation, dominating the sum and pulling skewness positive. Step 4. Sum all cubed deviations. Step 5. Divide by n times sigma cubed to get the normalized skewness value. Our result is approximately 1.119. Moderately positive skew. This confirms what we can see intuitively. The outlier of 12 has dragged the mean above the median, creating an asymmetric right tail. Now let's tackle kurtosis, the second shape descriptor. While skewness describes asymmetry, kurtosis describes the tails and the peak of the distribution. The formula uses the fourth central moment divided by sigma to the fourth power. Using the fourth power means all deviations contribute positively, and extreme values in the tails are amplified enormously. A value twice as far from the mean contributes 16 times more to kurtosis than variance. A critical practical note: the normal distribution has a kurtosis of exactly 3. Most software, including Python, CP and Pandas, reports excess kurtosis, which subtracts 3 from the result. So excess kurtosis of 0 means your data has normal-like tails. Always check which version your software is reporting. There are 3 kurtosis types, each with a distinctive visual signature. Mesokurtic in teal is the baseline, the normal distribution with excess kurtosis of 0. Leptokurtic in red has positive excess kurtosis. meaning higher than normal. It has a sharper, taller peak and much heavier tails. This is crucial. Leptokurtic distributions produce more extreme outliers than you'd expect from a normal distribution. Financial returns are leptokurtic. Market crashes happen far more often than normal models predict. Platykurtic in purple has negative excess kurtosis. It has a flatter, broader peak and thinner, lighter tails. Values cluster less around the mean and more in the shoulders of the distribution. The uniform distribution is the extreme platykurtic example. Look carefully at the tails beyond 2 standard deviations. The red leptokurtic curve sits noticeably above the teal normal curve. This gap represents the excess probability of extreme events. In finance, this is called fat tails. And ignoring them has caused real disasters. Long-term capital management's 1998 collapse and the 2008 financial crisis both involved models that assumed normal distributions when the true distributions were leptokurtic. Here's the reference table for kurtosis. Leptokurtic distributions have regular kurtosis greater than 3, excess kurtosis greater than 0, and are described as having heavy or fat tails. Mesokurtic is the normal baseline at kurtosis exactly 3, excess kurtosis 0. Platykurtic distributions have kurtosis less than 3, negative excess kurtosis, and thin or light tails. In practice, financial return data is almost always leptokurtic. Stocks and currencies experience extreme moves far more often than a normal model predicts. Bounded datasets like exam scores tend to be platykurtic. There's a ceiling of 100 that prevents extreme high values. Let's compute kurtosis for the same dataset. 2, 3, 4, 4, 5, 5, 5, 6, 7, 8, 12. The mean is 5.55 and sigma is 2.6064. Step 3 is where it gets interesting. We compute the fourth power of each deviation. Crucially, the outlier score of 12 has a deviation of 6.45 from the mean. 6.45 to the fourth power is approximately 1729. Dwarfing contributions from all other data points combined. This shows why kurtosis is so sensitive to extreme values. The regular kurtosis is 3.9163. Subtracting 3 gives excess kurtosis of 0.9163. Since this is positive, our distribution is leptokurtic, heavier tailed than normal, driven by that single outlier of 12. Let's examine how skewness and kurtosis concretely affect machine learning models. Linear regression assumes normally distributed residuals. High skewness or excess kurtosis in your residuals invalidates p-values and confidence intervals. Logistic regression converges slower with skewed features, requiring normalization. Neural networks suffer vanishing gradients when input features are heavily skewed. Batch normalization helps, but transforming inputs beforehand is better practice. Decision trees are the good news. Split-based methods are naturally robust to skewness, though extreme outliers can create unnecessarily deep trees. K-means assumes spherical clusters of similar size. Heavy-tailed leptokurtic distributions cause centroids to become unstable. Gaussian naive Bayes explicitly models each feature as normal. Violated normality severely degrades classification performance. Support vector machines need well-behaved feature spaces. Transformations improve the clarity of the decision margin. And for anomaly detection, kurtosis itself becomes a feature. Leptokurtic data generates more extreme values that may trigger false alarms. When your data is too skewed for your model's assumptions, transformations are the solution. For mild positive skew, a square root transformation gently compresses the right tail. For moderate positive skew, like income data, the logarithm transformation is the workhorse. If your data has zeros, use log of x plus 1 to avoid undefined values. For severe positive skew, inverse or inverse square root transformations can be powerful. The Box-Cox transformation is a flexible general-purpose tool that optimizes lambda to find the best power transformation for your specific data. Lambda equals 0 gives you the log transformation. Other lambda values give different power transformations. Yeo-Johnson extends Box-Cox to handle negative values as well. In Python, SciPy, stats provides Box-Cox and Yeo-Johnson functions. After transforming, always check the skewness and kurtosis again to verify improvement. Let's bring everything together with a real case study. Salary data at a tech company. Most employees earn between $60,000 and $100,000. But a few executives earn between $500,000 and $2 million. Looking at the raw salary statistics, the mean of $98,000 is badly misleading. 75% of employees actually earn below the mean. Skewness of 2.84 confirms severe positive skew. Excess kurtosis of 9.2 means extremely heavy tails. Far more extreme salaries than normal. Now apply a log transformation. Skewness drops from 2.84 to just 0.12. Practically symmetric. Excess kurtosis falls from 9.2 to 0.3. Essentially mesokurtic. The most striking result. A linear regression predicting salary from experience and education achieves R² of only 51% on raw salaries, but 79% on log transformed salaries. That 28 percentage point improvement came purely from addressing skewness and kurtosis. This is why distribution shape is critical for model performance. Here is your complete reference table for skewness and kurtosis. Skewness uses the third standardized moment. Normal distributions have skewness of 0. Positive skewness means right tail. Mean is pulled above median and mode. Negative skewness means left tail. Mean falls below median and mode. Kurtosis uses the fourth standardized moment. Normal distributions have kurtosis of 3. Leptokurtic means fat tails. More outliers than normal. Platykurtic means thin tails. Fewer outliers than normal. Remember, Python, SciPy and Pandas report excess kurtosis. They subtract 3 automatically. Keep this table as a reference whenever you analyze distribution shapes. Let's wrap up with 10 essential takeaways. Skewness tells you the direction of asymmetry, which way the tail points. Kurtosis tells you about the extremes, how fat or thin the tails are. For right skewed data, mean exceeds median exceeds mode. For left skewed data, the order reverses. Leptokurtic distributions are everywhere in finance. Never assume normality for returns. Platykurtic distributions have bounded ranges that prevent extreme values. Python reports excess kurtosis, so normal distributions give 0, not 3. Skewed inputs violate the assumptions of linear regression, naive Bayes, and Gaussian models. Transformations like log, square root, and Box-Cox are powerful remedies. And above all, always start with a histogram and QQ plot. Visual inspection before modeling is the single most important habit you can develop as a data scientist. Congratulations! You've mastered skewness and kurtosis. You now understand how to measure distribution asymmetry and tail behavior. Interpret the numbers. Visualize the shapes, apply appropriate transformations, and understand exactly how shape affects machine learning model performance. These two measures are often overlooked, but they reveal what summary statistics hide. Check the next video in the series for our deep dive into correlation and covariance. If this helped your understanding, please like and subscribe. It helps the channel grow. Drop a comment below with any questions, or let me know which Day 10 topic you're most excited about. See you in the next one.